Hello everybody, welcome back to another video. Today we're going to be solving the AP Calculus BC FRQ number 2. Let's get right into it. It's been a while since I posted a video, but I hope that's fine. AP season is now over. Good job everybody on your AP exams. But yeah, you can check your answers by seeing what you went wrong or if you remember it. Alright, so here's the problem. A curve C is defined by the polar equation r of theta is equal to 2 sine squared theta for 0 is less than equal to theta, which is less than equal to pi. Curve C and the semicircle r is equal to 1/2 for 0 is less than equal to theta, which is less than equal to pi, are shown in the xy plane. So we have a Cartesian graph here, and this is a polar graph, which we can see right here, defined by two equations, r of theta and r is equal to 1/2. So our curve C is this big thing, which is going like this, and then our r equals 1/2 is right here. Now, part A of this problem says, find the rate of change of r with respect to theta at the point on curve C where theta is equal to 1.3. Show the setup for your calculations. If you don't understand this, I suggest you pause the video and take a second to internalize this if you haven't taken this. But essentially, we have a curve right here. They want us to find the rate of change of r. So one thing that many people got wrong was immediately they thought, okay, we see rate of change. This must mean derivative. I'm a calc student, so I'm going to think this is the slope of the tangent line. We're going to find the slope of the tangent line was theta is equal to 1.3. Somewhere here maybe, like at this point, possibly find the tangent line. No, that's not what this question is asking. Specifically, if you read it precisely, it says find the rate of change of r with respect to theta. So that means when we have theta is equal to 1.3, wherever that value is, well, I could actually check. Pi over 2 is about 1.5. So yeah, 1.3 should be right here. It wants us to find the rate of change of r. So does that mean that r is increasing or is it decreasing? Well, we know that this is a distance right here. We can call this a. And we know that it's at this point, which is where it's going to, must be longer than this point A. You can just visually see it. It kind of looks like it. So we know that our derivative is going to be positive because r is increasing here. The distance from the origin is definitely increasing at that point. So that is something you should always do to see in your mind, hey, am I internalizing this correctly? This is a way to check your answer. But to actually solve this, it's very easy. Let's write it right here. I'll shift it down later. All you have to do is the derivative. It's r prime. So yeah, you have r of theta is equal to this, which is our curve C. R prime of theta, r prime of theta is going to be equal. We have 4, we bring this down, sine of theta, and then chain rule, we take the derivative of this, cosine of theta. Just like that. Then we take r prime of 1.3, because that's what the question asks, and then we get 4 sine of 1.3, cosine of 1.3. And this value is approximately 1.031. There you go. So that is part A. And then they ask you for the setup, so you have to show how you got r prime and all that. You can't just write a blank answer. So if you did that, you probably got points marked off. Part B, find the area of the region that lies inside curve C, but outside the graph of the polar equation r equals 1/2. Show the setup. Many people got this part of the question wrong, and let's see what it's asking. It wants us to find what's inside of curve C, but not within the circle 1/2. So let's draw this. I'm going to quickly shade this in. This is what's in curve C, and this is not in the curve 1/2. So I'm going to draw this in red. This is the part that is also in curve C, but they don't want us to include that. So let's analyze this point right here and this point right here. We're going to find these points of intersection, but first we have to understand how we're supposed to calculate this area. We can simply calculate the area of curve C by doing this. Let's say we started from whatever point this is, theta is equal to A, whatever. We can call this angle A. We can say theta is equal to A at that point. And then we're going to be adding up all the values like this. So I'm going to be summing as theta increases, theta increases, theta increases, theta increases. And then I get to this point, and then I stop again. And then I don't need to do anything more. And I'm done because I got all of the area in this blue area. I got all of that. But what do we have left to do? We have to subtract the area here. But here's a very important part. I know it got really messy, but if you look at the point of intersection, I started from here to here. This does not include this minimal area that is under the orange line. Something to just internally note here. It's important when solving the problem. And same on this side. when we stop at that point of intersection, we're not including that point right here. So people got confused by this and started summing or subtracting from point theta equals 0, assuming that they have to subtract whatever is in curve C. They got very confused. So that's all it's asking. We just start summing from here and go to here. And then we sum this, and then we subtract that. That's literally it. So part B is as follows. All we have is area. I like to write A. What is our formula? We have 1/2 integral of r of theta squared. That is the formula for an area of sector, d theta. So we can write this quite cleanly by writing it like this. We have the integral from pi over 6 to 5 pi over 6 of what? 1/2, and I'm going to explain this in just a second, r of theta, just like this, squared. And what do we have to do? Subtract 1/2 squared d theta. Okay, a lot going on here. I already put the points of intersection, but it's quite easy to find them. We know our curve C is 2 sine squared theta, and we're trying to find the point of intersection. When is it equal at those points? I'm going to clean this up just a bit. Actually, let me just do this. That's what we're trying to find. There we go. Yeah, so just like that. Yeah, we just have to find those points of intersection by setting the two equations equal to each other. 2 sine squared theta is going to equal 1/2, and 1/2 isn't just anything, it's this equation right here. Let's solve for theta. We have sine squared theta is equal to 1/4. Don't forget your algebra. Then we have sine of theta is equal to 1/2. Obviously, that'll give us theta is equal to pi over 6 and 5 pi over 6, just like that. And that's how I got these bounds right here. You plug that in. Now, let's see, did I get it? Yeah, I got it. So you'll see right here, I put a 1/2. That's because area is equal to 1/2 integral of r of theta squared d theta. So that's the 1/2 right there. Then where I put parentheses, our r squared of theta is this thing we're summing up right here. So we're summing up, as I said, we're summing up like this. We're summing up all of that. And then at the end, we subtract what happens from here to here within the circle of r equals 1/2, just like that. So that's why we're subtracting right here. If this is a little bit confusing, I can definitely write it out like this. I have 1/2 the integral from pi over 6 to 5 pi over 6. First off, we're summing the curve C. That would be r squared of theta d theta. And then I want to subtract 1/2 the integral from pi over 6 to, pi over 6 to 5 pi over 6, same bounds, like this, of 1/2 squared d theta, just like that. That's the same thing conceptually going on. And you can simplify it into that. Way neater. So yeah, once you do this, let me see what I had here. You should get approximately 2.067, but pretty remarkable if you remember that. All right, moving forward to part C. By the way, part B was definitely the most difficult, but part C also tripped some people up. It can be shown that dx d theta, the change in x over the change in theta, is 4 sine theta cosine squared theta minus 2 sine cubed theta for curve C. For 0 is less than theta, which is less than equal to theta, which is less than equal to pi over 2. Find the value of theta that corresponds to the point on the curve C that is farthest from the y-axis. Justify your answer. Again, College Board likes to confuse you by using some weird terminology and just fancy language to make it seem a lot more complicated than it is. All this is saying is analyze this carefully. This is not dr d theta, this is not dy d theta, this is dx d theta. What is the change in x with the change in theta? We have this equation describing the rate of change of x, not the actual x value. We have our bounds, obviously, and we want the theta value that tells us when the point is farthest from the y-axis. What's the y-axis? This is how you should be doing conceptually. This is the y-axis. Farthest means that we are maximizing the x value, either here or here. But they told us our bounds are from 0 to pi over 2, so we're only looking in quadrant 1. So I can draw a little thing here, this to this. That's it. So there we go. Now we just want to maximize some point right here. It's probably about there. So what's that theta value? Well, I'm sure you learned this, but when you have a derivative of any function, this is completely separate, not part of this, and I have it right here, the derivative is equal to 0 at that point. And that's some kind of extrema. That could be a relative minimum, that could be a maximum, that could be a variety of things. So we can use this to our advantage here. We know that the x value, if you want to look at it from a derivative standpoint, the x value is increasing as theta increases. So as theta is turning this way, just conceptualize this. As theta is turning, and is at this point, it starts like this. The x value is increasing. I'm talking about like this value right here. It's increasing, increasing, increasing. And all of a sudden, it starts decreasing, decreasing, decreasing. So we know, and this is only for quadrant 1. So we know if the derivative is equal to 0, it's guaranteed that that's going to be a maximum. So let's just do that. And they give us the derivative right there. So there's nothing complicated we have to do. So part C, just let dx d theta simply equal 0. It's that simple. And I believe this is a, this is a calculator allowed question. So you can literally just plug this into your calculator and solve for it and use the calculator functionality and go to 0 to see when it's equal to 0. But you can also do this analytically if you want. 4 sine theta cosine squared theta minus 2 sine cubed theta is equal to 0. You want to just do 4 sine theta cosine squared theta is equal to 2 sine cubed theta. Ooh, that's not a cube. Cube theta. Then we have 4 cosine squared theta is equal to 2 sine squared theta. Then we just have 2 is equal to tangent squared theta. Then we have tangent theta is equal to root 2. This is what you can plug into your calculator for simplicity. But then you have theta is just equal to arctan of that, which is about 0.955. So that concludes part C, and hopefully you got that right. It was honestly a really easy problem. It's understanding conceptually is one of the biggest things. Just slow down, think about it, and then you're good. Finally, part D. So B and D were the hardest parts for sure. D, let's get into it. A particle travels along curve C. Okay, we're going on the big curve. So that d theta dt, the change in theta per change in time is equal to 15 for all t. Find the rate at which the particle's distance from the origin, so r, changes with respect to time. So this is dt. When the particle is at point where theta is equal to 1.3. Show the setup. All right. So they want us to find the change in the particle's distance, dr, with respect to time, right there. dt, just like that. So we have dr dt. Now, if we look at the original problem statement, we have r of theta. The derivative would be dr d theta. And what do they give us in the problem? They give us d theta dt. So if you're a calc student, this should ring a bell immediately. We can use the chain rule. The chain rule states that we can simply do this. We have dr d theta, and we have d theta dt, which is given right here. This is equal to 15 all the time. If they give you something like this, you should be thinking, hey, this is not directly, you can't just plug it into dr dt, but what can I use to get dr dt immediately? So there you go. Once you get this, you're all set up to go. And we have dr d theta already. What was dr d theta? We calculated it up here. We have 4 sine theta cosine theta. So dr dt is equal to 4 sine theta cosine theta times 15, which is d theta dt. They want the rate of change of the okay, we got dr dt when the particle is at theta equals 1.3. All you got to do is plug in 1.3 and you're done. Dr dt at theta is equal to 1.3 is equal to 4 sine of 1.3 cosine of 1.3 times 15. And this gives approximately 15.465. Beautiful. Part D is honestly really easy. It was just getting that click for the chain rule, and that's all. So I hope you guys enjoyed this video. If I didn't explain something too clearly, leave a comment down below. I will definitely try to do better. Feedback is great. I really appreciate it. Future video ideas, let me know. I'm going to try to do the other FRQ problems as well. Let me know if that helps. Thank you guys for watching. Really appreciate it. Drop a like, subscribe. Thank you guys. See ya.